Great. So I would love to welcome Vincent Leys. He's the Senior Coastal Engineer with CBLC Consulting Engineers. And in the past 20 years, he has completed a wide range of projects throughout Atlantic Canada's diverse coastal communities, which require functional solutions to deal with dynamic shorelines, storm rise impacts, and sea levels. And today we're going to be getting into the nitty-gritty of a whole bunch of really exciting examples of using natural infrastructure and adaptations to deal with the impacts of sea level rise, a lot of which is to do with climate change. So I'm really excited to pass the mic over to Vincent, excuse me.
It can be both. It'll be Vincent tomorrow. Thanks everyone for being here. This is an exciting opportunity, and I'd like to thank the New Brunswick Environmental Network for inviting me for this talk. So let me start sharing my screen. Okay. Okay, everyone can see that?
Yeah.
Perfect. So, yeah, I'm an engineer. So I'm going to present a number of projects. Mute. Everyone can hear me, so I guess that message is a moot point. So yeah, so from an engineering standpoint, let's first look at what the project steps would entail. So as coastal engineers, we like to look at all the data that we can find on a site, which is really important for proper long-term solutions to design these things. So we're talking about erosion rates, waves and water levels, currents, soils, and sediment processes, because in the end, every site is unique, and that's what makes it interesting, is that there's no single solution that can be replicated exactly at another site. It all has to be site-specific, and it all depends on local conditions. So once we have all the data, then we use our calculations and our models to develop options towards design. So usually the design has to be picked from a range of possible options, and the choice would depend on things like cost, of course, would be a big one, but also permitting requirements, how it fits into the surrounding infrastructure, how it can be used by the public. So aesthetics is a big one as well. And of course, long-term durability in the face of rising sea levels and storms. So there's a variety of factors to take into account when picking an option. And then during the construction phase, it has to be carefully monitored as well, both during construction to make sure that it's built to specifications, and also post-construction monitoring. So that talk fits a bit in the monitoring part, because you'll see there's a number of slides on projects that have been carried out a couple of years ago where I like to stop by every time I go that way and take some pictures. So it's interesting to see the evolution of these things. So I'm going to take you through local examples using hybrid techniques combining rock, sand, and vegetation. The first one is going to be an example dealing with rock along a highway and pocket beaches at the entrance of Fundy National Park in New Brunswick. So that was done in 2018, built 2 years ago. Second, I'm going to show some examples of buried rock revetments, with notably an example in Pictou County, Nova Scotia, and another one in Cape Breton, Nova Scotia. And then finish that with an example of detached breakwaters, a pretty exciting project that was recently built out of Surrey, PEI. So as I mentioned in the preamble, for high-risk areas, you typically want to consider non-structural options first, because if it's high risk, chances are your coastal protection is going to be expensive, and sea level rise will eventually catch up to it in most cases. So you want to look at long-term planning, such as setbacks and managed retreat, and how practical it is to move vulnerable infrastructure and people away from shore. So that should be done before calling coastal engineers to figure out what an actual shoreline protection technique might look like. But for cases where the migration of property or infrastructure away from the shore is not a short-term option, then that's when engineering solutions can have a place. And there are a range of solutions that, with varying degrees of vegetation, soft versus hard rock structures. So that's what we're looking at here. And in this talk, I'm going to be talking primarily about hybrid techniques that combine some amount of rock and some amount of vegetation. So for very sheltered environments, you could probably get away with vegetation only, but for very, very exposed sites, your vegetation will sometimes not hold up to the wave action, and that's where you're into really heavy rock revetments or seawalls. So the first project we're looking at here is at Fundy National Park. So that's what the entrance looked like a couple of years ago. So you have essentially the highway to the entrance of the park built on a barrier beach. And the erosion of the barrier beach, it was eventually catching up to the road, which meant destabilizing the embankment. So there were some ad hoc repairs done over the years over the embankment, but it really needed a more long-term kind of solution. So here we're talking about an environment with 12-meter tides and very high waves that can hit the embankment at high tide. It's a beautiful site, 20 kilometers, a very dramatic shoreline, lots of neat hiking and biking trails through Acadian forests. So really a site that we want to preserve for the continued use and enjoyment of the public. That's an example of what the highway embankment looked like when we first took the site visit in 2016. So you can see here there's been some geotextile put in at some point with riprap revetment on top, but of course the magnitude of the storms meant that this was not stable enough to sustain really high storms. So a more permanent solution was being sought there. A long time ago, the road used to be to the back. So you had a very wide natural beach, and what was feeding the beach were eroding cliffs to the south, because here you have big waves coming from the south, eroding the cliffs and moving the sediment eroded from the cliffs onto the beach. But then what happened in the late 70s, 1980s is that these eroding cliffs got armored to preserve the area on top. So that cut off the sediment supply to the beach. And in combination to that, the road was built closer to the beach with the effect now that there was not enough sediment supply to keep the beach healthy and functioning. So that's what really caused the erosion. It's this combination of armoring up drift and then the road being ever closer to the ocean. So you can see here with shorelines from 1945 to 2016, there was a steady retreat of the high water mark towards the road. And the beach access happens to be where some of the erosion was the most severe. So that beach is iconic for the park, and it's really something that we wanted to preserve, is this nice beach access for visitors coming onto the park. Here's a photo from Parks Canada. I think that was in 2005 or 6, where there was a major storm there. And as you can see, the beach access structure got completely flooded by the large waves there. So a couple more years and that boardwalk would have been gone for sure. Another project constraint that we had there was to make sure we would preserve the integrity of a coastal lagoon that's just a little bit to the southwest of the highway embankment there. This is a lagoon that floods at high tide, but that is dry at most of the tidal stages. And there were a number of interesting grass species there, notably an endangered species called the Roland sea blight. So one objective of the project as well, especially it being in a national park, is to make sure that we preserve coastal processes that allow these rare plants to grow in that environment. One way to preserve coastal processes in places like that is to replicate the natural functioning of beaches. And you can see beaches like that all over the world. They're called pocket beaches, and they're typically controlled by non-erodible headlands. So you have waves breaking on a headland and then refracting around the headland. And as the waves make their way towards the shoreline, it tends to shape the shoreline in an equilibrium shape for places where there's mobile sand. And that's what's create these pocket beaches. And it's true also in the Bay of Fundy. This is in Horton to the northeast of Alma. And you can find these pocket beaches where the shape can be pretty well predicted by these equations that coastal scientists have developed to predict the shape of natural pocket beaches that would remain stable in the long term. So the shape of the beach is governed by the orientation of the headland and the distance between the two headlands and the distance between the headland and the deeper part of the beach. So these sort of empirical relationships can be very useful in establishing nature-based design to ensure that there is enough space for the beach to remain stable in the long term, even under sustained wave attack. So we use that for that site here. So there's guidance that have been developed by coastal scientists for designers. So it could be to reestablish an existing beach with some help with an artificial headland, or some places where they've actually built complete beaches where there was no beach before, but with artificial headlands and nearshore breakwaters. And the idea here is to promote the growth of the beach in the lee of the breakwater. And if it's sized properly, then you can expect a very stable shoreline shape for the long term. So one of the things we use a lot as engineers is tools to size these structures and to figure out what kind of rock would be stable under these extreme conditions. So as an example, we have wave models to predict the evolution of wave heights from the offshore to the near shore. So as you can see in this case, on the left-hand side, the highest waves are actually towards the north there, where we had that picture of the boardwalk being underwater. And on the right-hand side of the screen, these would be the storm currents generated by these breaking waves. So what happens here is that you have strong waves breaking at an angle with the shoreline, and it's these waves breaking at an angle that create a longshore current that will move the sediment along the shoreline. So that explains why the beach was being fed by the cliffs. So if you armor the cliffs on the updrift, then there's no sediment for the current to pick up except at the beach, and that's what causes the erosion. So these modeled waves and currents can be fed into even more complex models of marine bed evolution. So the colors here represent the contours of the water depth, and we use these models to recreate a 30-year prediction into the future of accelerated beach changes, and in that case at the lagoon. So you remember we had these endangered plant species that can only thrive at certain elevations in the intertidal zone. So we wanted to make sure that these elevations were maintained with the new design. So that's what we used to size these breakwaters there. So under existing conditions to the left, you would have that lagoon predicted to erode completely in the next couple decades. But by using the stable beach principles that I described, and then checking that into a computer model of accelerated erosion, we were able to determine what would be the correct sizing and spacing between these two breakwaters to conserve sediment within that pocket beach and to make sure that there would be a continued environment for these intertidal plant species to thrive. So a number of options there when it comes to the road. Number one would be to relocate the road away from the beach and size the breakwaters in order to obtain a stable beach shape. That option was not retained because of it was the highest cost option, number one, and number two, it was not a very desirable option in the short term because the road was recently new. So in order for an option to be acceptable, it's also nice if the implementation of the option would correspond to a typical rebuild or maintenance cycle, which was not the case here. So that was not retained, especially with the fact that the other option proved also quite feasible. Number two was the building of detached breakwaters off the road and the addition of sand nourishment. So with a typical site with moderate tidal range, that would typically be a very attractive option. And I'll show an example of that being done in PEI in a couple slides. But at that particular site, we're talking about 12-meter tidal range. So the further out you put the breakwaters, the more massive they become. And after sizing them, given the wave climate and the desired orientation of these beaches, the minimum elevation that you would need these breakwaters to be would be 5 meters. So at low tide, imagine you have people walking out the beach around these 5-meter tall rock mounds. So from a visitor experience and aesthetics standpoint, this was not the most desirable solution, especially given that it's a national park and we want to maintain the site as close to natural as possible. So that left us with the third feasible option, which is a rock revetment along the beach, along the road, sorry, and then using these breakwater extension as headland control for beaches, number one at the lagoon to the south and number two at the entrance to the north. The idea with these breakwater extensions is to create headland control that would keep the sediment contained within these particular cells. And with the stable beach principles, to keep the sediment contained, you don't need to have a continuous armoring all along the beach. You can size the breakwater headlands so that the beach stays contained, even if you have a sizable opening between two breakwaters. So that's the option that was retained, and construction took place in the early part of 2018. Here we're looking at the rock revetment along the road looking towards the lagoon. So you can see the break and the breakwater there towards the lagoon. The key principle during construction was to maximize the reuse of local materials. For example, the local riprap and rock were reused in the construction. The new breakwaters had their toe excavated to ensure stability, and the sand from that excavation was used as beach fill for the renourished beaches there. And then the marron grass was replanted in the spring, just at the end of construction. In the contract, we took great care that the contractor doesn't disturb sensitive plant areas. And the other interesting thing to mention is that under the rock, we use the geogrid layer to mitigate the settling of rock structures, because in some of these projects, if you lay the rock directly onto the sand or onto the seabed there, chances are it's going to settle at some point. So that's one key improvement to make in such projects. So that just made it to Google Earth. You can see here the rock structures along the highway with the large openings for the lagoon to allow tidal circulation, and the end of the breakwater at the beach there to the north, with the inclusion of a brand new boardwalk as well. And so that picture at the bottom was taken by Doug Watson of Parks Canada just recently in April, and things look really good. People seem to be enjoying the site. The new boardwalk is pretty popular, and there's no risk of erosion now at the beach access point, which is a key thing. So that's what it looked like in the fall of 2018, a couple months after construction. And now in 2020, here we are. So things are pretty stable. There's a little bit of sand accumulation inside the beach, which is good, but we're not expecting the beach to grow because, as I said, due to all the updrift armoring that happened over the years, there is no significant new sand source to nourish the beach. But the idea here, at least, is to contain the sand where it's at. Now, this is a film I obtained from the local harbor authority during a big storm last fall. So you can see the revetment working as intended to mitigate overtopping onto the road. And this is the beach section. And as you can see, the beach is probably the most effective in dissipating the wave action. Wherever you have space, it's best to use a beach as a natural solution for wave dissipation. That's really what works best. Where you want to use rock is for situations where you don't have enough space for a beach, for a stable beach to develop, which was the case along the highway and just in front of the beach access point at the boardwalk there. But anywhere else, if there's room, a beach is really the best solution for attenuating wave energy. So now let's leave New Brunswick, and we're going to go back to Nova Scotia and talk about buried revetments, which is another concept that's being used at a couple sites in the Maritimes. So a buried revetment is essentially an enhanced version of a rock revetment, which is naturalized, so to speak. So in this concept, the buried rock revetment acts as a last line of defense against erosion. The premise being that you're going to nourish your dune with new sand and new grass, and then up to a point where the erosion catches up with the rock revetment, and then it's time for added nourishment. The rock revetment doesn't slow down the erosion. It doesn't change the sediment transport characteristics of your site. It's a last line of defense. But with the beach nourishment and the planting of grass, you can considerably slow down erosion before it even reaches the rock revetment. So that's the first example. That's at Lighthouse Beach in Nova Scotia. This project was commissioned by the Nova Scotia Department of Transportation. That beach was a low-lying barrier beach, and it was prone to breaching very often, which was causing increased wave action in the lagoon in the back. So the solution there was a buried revetment to recreate the barrier beach and to prevent it from breaching, essentially, and to naturalize it with sand and grass on top. So after it was built, you couldn't see the rock, but a couple of years after that, the toe of the armor stone is starting to appear, although the back of the dune still looks very healthy. So that's fairly typical of how buried revetments are supposed to work. If you have a site with ongoing erosion problems, the solution will not slow down the erosion, but at least it will strengthen your area and prevent it from catastrophic breach or failure. So that's 6 years after construction. I haven't been to the site recently, but certainly next time I drive to Cape Breton, it's a good place to stop there. Another example of buried revetments was at Dominion Beach Provincial Park. So that's the most popular beach park that's close to Sydney in Cape Breton, Nova Scotia. That beach is extremely exposed to the Cabot Strait. Very large storms there. That's a storm picture in 2010 that I got from the locals. 2012, you can see there was a boardwalk that got completely washed out. And so a boardwalk can be replaced, but when it comes to endangering the beach buildings, change rooms and showers and facilities, that's where the red flags came up. And we were seeking a more permanent solution there. Because of the extremely large wave exposure and the desire to maintain sort of a natural look to the beach, the idea, for example, of offshore breakwaters was not retained for that site. And the concept of the buried revetment made pretty good sense. So that what was built to protect the parking lot and the building. So we're talking about the first 300 meters of beach there. That barrier beach is several kilometers long. So of course, we were not going to build the revetment along the whole length because it would be prohibitively expensive. But we built it for the first 300 meters there. So that's what it looked like immediately after construction. So done properly, you have the sand covering the rock, and then you start planting vegetation on the back of it to strengthen it. So of course it always looks amazing right after construction, but then number of years pass by, and that's when the storms start reaching the rocks. So a little bit like the Lighthouse Beach example there, after a while the rocks start showing up because the buried revetment itself does not slow down the erosion rate. So that was 2 years ago. But the rock revetment is doing its job. It's preventing breaches, and the trail to the back is fully protected. So, and it's got good vegetation. So it's a pretty good hybrid solution because you get protection from surges and overtopping. You get the more natural look, except when you're on the ocean side of the beach, you can see some of the rocks, but it's a pretty good compromise sort of solution. In December 2018, there was a huge storm that actually exposed the end of the buried revetment. And you can see there in this drone picture, where the buried revetment stops is where the overwash started. So there's a debate right now as to whether or not this revetment should be extended out, at least to the little bridge there, because it's a very popular local trail, and you can do a loop from the back of the beach, then on the bridge, and then to the end. The alternative to extending the buried revetments is simply, every time there's a major storm like that, to scoop up the gravel with a small excavator and artificially rebuild the gravel berm as sort of a continuation of the buried revetment. So it's more maintenance, but it's certainly, one maintenance operation is certainly a lot less than the buildup of the buried revetments along several more 100 meters. So these are sort of the pros and cons there that you're dealing with it in such sites. These are sites where it's extremely difficult to maintain a stable trail position when you have such dynamic natural processes.
If I could just break in here, it looks like we have a question from William.
Yeah.
In the chat there.
Okay.
It says, if only partial work or extension of revetment, does that contribute to greater erosion of adjacent shore?
So in cases where you have sediment moving along the shoreline, yes, because imagine if we had a revetment along a cliff that would feed the beach down-drift, that would be true. So for example, in the Fundy National Park Alma example, the armoring of the cliffs to the south over the long term contributed to beach erosion to the north, because you have waves that are traveling clearly from south to north. In this particular case, the waves are pretty perpendicular to the shoreline. So you can see the wave crest there hitting the shoreline straight. So most of the erosion actually comes from a cross-shore process. So you have waves overwashing the beach, and the erosion is actually transporting the sediment over the barrier beach as opposed to alongside it. And the other thing that contributed to erosion there is that the cliffs that historically fed that beach were armored on the east side. And now that armoring supports a parking lot and a number of properties, so it wasn't in the cards to remove the armoring to feed the beach. So the particular armoring at the buried revetment does not accelerate the beach erosion to the north, but what had been done historically, which is armoring of the cliffs and sand mining on the beach, did contribute to ongoing erosion. That's correct. Okay, so that was a great question. Thank you. Last example with another concept here is the concept of nearshore breakwaters. So that's the most recent project of the ones we're talking about here. That was led by the PEI Department of Transportation, Infrastructure and Energy with design inputs from Coldwater Consulting. So the problem here was that until a few years ago, the erosion was getting closer and closer to the causeway in Surrey. So the town had built this nice little beach park with a parking lot and really nice facilities there for those who go to the ferry to the Magdalen Islands, like I try to do a few summers. It's a great place to stop and enjoy the beach before the ferry leaves. And unfortunately, erosion was catching up to these facilities. In this case, the sediment transport is going from east to west. So a solution was being sought there to capture some of that sediment transport going from east to west and use it to grow the beach in a natural way. And the tidal range here is pretty moderate. So is the wave action. So it was an ideal site for this concept of nearshore breakwaters. And as you can see there at the bottom, 2 nearshore breakwaters were built. It's a pilot project, so the department is currently monitoring how it's doing with the growth of the beach, but so far it's working as designed. This is a picture I took at low tide last year and then another one at high tide. So you can see they're intertidal reefs. The one interesting design aspect of these breakwaters is they were built with local sandstone. So we're not talking about trucking expensive armor stone from New Brunswick there. It's all local stone. Granted, it's a little more erodible than your typical armor stone that you'd find in New Brunswick or Nova Scotia. But the idea here is that over the long term, yes, that armor stone may erode, but the product of that erosion would feed the beach, so it's not entirely lost. We're talking about a 1.6 meter tidal range with large intertidal flats, so it's a good area to put it because the nearshore breakwaters don't have to be very high to deal with the tidal range. And as you can see, since construction, there's already been deposition of sediments behind the reefs to help the beach grow. And it provides also a natural environment for benthic flora to grow. So that's an exciting pilot project that the department is watching closely in PEI. So in conclusion, for highly exposed coastlines, if non-structural options are not practical for the short term, effective protection is really best achieved by nature-based hybrid designs combining rock, beaches, and vegetation. And as we saw from these couple examples, if you have a nice, gently sloping beach, that's really your best solution for dissipation of wave energy. That beach can be reinforced by vegetation. And as a last resort, for places where you don't have the space for a beach or where you want to provide a last line of defense under the sand, then that's a good place for rock to be used. And to support engineering design for these projects, it's critical to have a really good understanding of coastal processes in terms of how the sand is moving and how the waves and tides are affecting the movement of the sand and how they're going to be impacting your design parameters. So I hope that was informative and interesting, and I'm certainly open to questions. Be glad to discuss that with you guys.
Wonderful. Thank you so much. We are going to just unmute everybody, and people can raise their hand or just unmute if they have a question or something that they would like to ask or a comment or anything like that. We are still recording, but let us know if we should pause, and you can also type in the chat as well. And I know it often does take a second, but okay, quiet bunch. Well, in that case, maybe it's time to close for the day. Great. So thank you so much for the presentation, Vincent, and we are meeting again tomorrow for the French language version of this. If there's anybody that you know that would like to take part, then please do send the link along. And oh no, Brandon, everybody should be able to unmute. You just have to choose, I believe. Oh, maybe. Ooh, is it possible that I'm mistaken? Oh, Emile Labrec says, could you give us an idea of the cost range of those solutions? And in the meantime, Brandon, I'm going to figure out why you weren't able to unmute.
Yeah, no, I was trying to unmute, but it wasn't allowing me for a moment.
Oh, I see. Yeah.
Yeah. So for any time where you have heavy rock along exposed shoreline, you're talking about several $1,000s per meter of protection.
Sorry, Vincent, the sound has cut out. Could you restart that? And there we go.
Okay, is everyone hearing me?
I can hear you.
Yeah.
Okay. So we're talking about for very exposed site that involve construction of revetments or breakwaters, we're talking about several $1,000s per meter of shoreline. So so let's say between $1,000 and $5,000 per meter of shoreline, depending on the site. So if you have 100 meters, that's anywhere from $100,000 to $500,000. So so it really depends on the length. But you're easily for more than 100 or 200 meters, you're easily into the $1 million range. I know the Surrey breakwaters were quite a bit less than that, a couple $100,000. I don't have the exact value here, but that's because they were able to reduce the amount of rock by placing the rock strategically offshore with gaps. And we were able to do that with the Fundy project by increasing the gaps between the rock, but there are still a fair amount of distance to cover with straight revetments. So in these cases, you're into really expensive projects for sure. So that's why at the opening of the talk, I mentioned that if you can consider non-structural alternatives first, it's always preferred because it'll be cheaper and a lot easier to maintain in the long term.
Awesome. Brandon, did you have a question now that you have unmuted capabilities?
Yeah, thank you. Yeah, so thank you, Vincent. That was an excellent presentation. And
Thank you.
looking at some of these slide pictures you brought along with it. It's really good to actually see some of these on the ground examples. I didn't know about the Alma one and the Fundy one, so
Yeah.
I think that's excellent. Maybe a larger kind of a bird's eye view question from your experience on these. Do you find you're running into more demand for natural or hybridized solutions to these problems than maybe you were in the past? Is there more
Yes, because
flexibility?
yeah, I think so. And there's more awareness of it. Um, there's always a desire to reduce cost as well. So anytime where you can reduce the amount of rock that's being used, that will typically reduce your cost. So that's one thing. And then any opportunity to use vegetation is encouraged more and more. For example, from the point of view of carbon credits, if you can have a project that demonstrates that it's going to stabilize a salt marsh or have more dune grass growing, that's an element of carbon capture that is nice to include in your project benefits as well. The other thing is having rock as habitat, for example, for the Surrey breakwaters. So there's all these ecological considerations that are important nowadays to include in a project as well.
That's a great point. I know talking about these kind of solutions when we talk to communities and some of the municipalities on alternative approaches, that co-benefits question does, or that answer for co-benefits does come up quite often. And I guess I don't know if you experience on your side, but sometimes there's a real, almost like a light bulb moment when you consider
Yeah.
some of the other, maybe, I don't know if it'd be holistic effects, but some of the other co-benefits that might not even have been considered.
Yeah, that's true. Yeah, sometimes for smaller projects, one of the added difficulties with these hybrid approaches is that in order to reduce wave energy, you want to have flatter slopes. That's really one of the key concepts. And in order to have a flatter slope, you need space across the shore. And for places where you don't have a lot of space, say your infrastructure is very close to the bluff, for example, that means you have to go out into the water. And that entails a fair amount of permitting that is sometimes not desirable from the owner's standpoint. So that's an added complication there. So sometimes it's easier to just dump armor stone along the bluff and remain above the high water mark rather than do a more complex project and have the armor stone extend a bit in the water and have beach nourishment on top of that, because then you're running into permitting and habitat and that. So there are a lot of aspects to consider.
Awesome, thank you. We have a question here typed from Nancy. She's saying, what are the green options for a place that doesn't have a sloping beach, such as a shore like Annapolis Royal, Ketch Harbor, Liverpool's downtown core? It's rocky, an abrupt stop to the ocean, facing sea level rise, storm surge, and coastal flooding.
Yeah, well, in places where you don't have the option of having a flatter slope, these are the more complex ones, because then you're talking either about completely blocking wave energy through a near vertical seawall, for example, but that becomes very expensive and you have to keep raising it with sea level rise. The alternative to that is to consider adapting your infrastructure to occasional flooding. For example, you can site new developments so that your parking garage can be flooded, for example, or you can start looking at how to raise certain pieces of infrastructure. Because in the end, if the site is low-lying and very exposed to waves, and if you don't have a lot of space to break the wave energy, and if going out into the water to create that slope is not an option, then you're into either very expensive seawall type solutions or raising your infrastructure. If migration is not an option, of course.
Awesome. Okay, Fushi had a question next.
No, I just opened my eye. Very beautiful projects. They are very interesting. Very good for the maritime. My field is more in the hydraulic engineering, so this area is pretty new to me. Very interesting. Very good. Thank you.
Thank you.
Wow, thanks so much. I'm glad you enjoyed it.
Thank you.
Leanne? Oh, Leanne just says thank you, and that it's interesting. So the next person would be Michael, and then we have a comment from, I think it says Evan.
Thank you. And yes, thank you for a great presentation, first and foremost. My question might have already, it was addressed a little bit in Brandon's response, but when it comes to proposing either hybrid or green infrastructure solutions, you mentioned keeping costs down and focusing on co-benefit. Is there any other, not angles, that's not the right way to put it, but is there any other types of things you try to include when trying to really show the benefits of those two types of solutions?
So we've talked about benefits, first of all, functional for coastal protection, and then co-benefits with ecological functions. Perhaps a third one that's extremely important as well is visitor experience and public use. All these projects here that I described are public infrastructure, so it's important to consider continued enjoyment of the public to the beach facilities and making sure it blends into the natural environment, because you don't want to ruin the experience of people visiting with large coastal structures that would seem out of place. So the trick is to be able to have something that does the job, but that still looks natural within the site that you're trying to mitigate, to fix, essentially, right?
No, that's great. It's not an angle I had thought of, so thank you very much.
Okay.
Awesome. So Evan says thank you, that this was a great presentation. I'm really glad to hear that this will be helpful for your visitor areas. That's awesome. Are there any other questions? Oh, Evan just raised their hand. Go ahead.
Hi, Vincent. This is Evan here at Fundy National Park.
Hi.
Yeah,
You
so
know all about it.
it was pretty. Yeah, it was pretty definitely relevant for me to sit in on this one there today. So that was an awesome, awesome surprise. So thanks a lot for that. I guess a question or maybe a comment I had. You know, I saw the pictures of the beach, and the fact that there's a working wharf with lobster and scallop fisheries right next to the beach. Just wondering what kind of considerations, or maybe was there an environmental versus economic issue in consideration of the boats that leave and come back on a daily cycle?
So you're talking about the harbor project. If the harbor project had a bearing on the parks project?
Yeah, because I'm just like, I noticed like the positionment of the breakwaters for environmental concerns.
Yeah.
But then I noticed that there's another breakwater on the other side of the harbor where the boats are. Were you involved with that one also?
Yeah. So that breakwater was designed to mitigate wave agitation into the harbor. So what happened is they expanded the harbor into the area that was not as well protected, and realized that the wharf was non-functional because of excessive wave agitation. So they added an additional breakwater to to reduce the wave action inside the harbor.
Okay, cool. And for those of you that are on the line, I know Vincent had some awesome pictures there, but just to give you an idea, when we were seeing these trucks come in, like with the actual rock and stone, like you're talking huge rocks, like there'd be maybe 2 or 3 on a transport truck. That's how humongous these rocks are. So it's a pretty impressive project, and it surely changed the beach. But I'm really glad to be on this call here today, because it'll kind of help the staff interpret what was done and the reasons for it. So thanks again for doing that. I might email you, Vincent, for some of those pictures later, if that's okay with you, just to
Sure,
chat
no
on.
problem.
Awesome.
Most of them are from your colleague Doug Watson anyway, so.
Okay, perfect. Awesome, thanks again.
Yeah, thank you.
Wonderful. Are there any more questions or comments?
Vincent, so in terms of the sea level rise, so in your opinion, in the next 10 days, 10 years, 50 years, big project or big problem should be addressed along the maritime coastline? What's the prospect? What do you think with your knowledge?
So I understand the question was on sea level rise.
Yeah.
And, I think the important thing when planning for these solutions is to always have the long term in mind and think, okay, when by the end of the lifetime, how do we keep these projects functional in the light of rising sea levels? So when you're talking about, for example, the road embankment at Fundy, part of dealing with sea level rise is making sure that it can be later raised to accommodate rising sea levels. One of the design constraints we had for the revetment along the road is to keep it low enough so that people would still see the views of the mudflats when driving in their car from the opposite lane. So we had a view plane analysis, which ended up requiring that the revetment was lower than we would have hoped for wave overtopping using traditional design. So the alternative was to make it a bit wider to have the road further away from the wave action. And by making it a bit wider, not only do you reduce overtopping by not having to have it as high, but you also allow for future raising. Because see, the further your crest is away from the infrastructure, the more room you have to raise it and catch up with sea level rise. So the idea here is that at the next maintenance cycle for the road, within 10, 20, or 30 years, when they eventually raise the road, then the rock revetment can be raised at the same time, and there's enough space to do that because we placed it sufficiently far away from the road and with a wide crest. So that's an example of adaptive design to show that you can plan for future upgrades in your infrastructure, because you want it to be functional for today's sea level. You don't want it wouldn't make sense to design it for a sea level that's only coming in 100 years in terms of final elevation, but you want to have some space in the design to be able to upgrade it when required.
So are there many locations like the Nova Scotia, the road need to be relocated or be raised in the near future?
These coastal roads built on low-lying beaches are actually a fairly common problem. That there's a number of examples across the Maritimes. So at some sites, it's feasible to reroute or relocate or abandon them, but at some other sites, like at Fundy, it's more difficult. So when you're looking at structural options like that, it's only for sites where relocation of the road is just not practical.
Okay, thank you. This is really interesting topic. Thank you.
Thank you.
Okay, so with that final comment and question, it looks like that brings us exactly to 3 o'clock. So I applaud everybody in attendance for your perfect punctuality. Thank you so much for joining, and this was really enjoyable for me. I hope it was helpful for everybody as well. We will be sending out the link to the YouTube video once the recording is available, and I think we can possibly get a copy of the slides, Vincent, if that's okay, like a PDF
Yeah.
of them to
Yeah.
circulate to everybody who attended, just in case that's helpful. And we do hope that you are able to join us for the next installment of this series on sea level rise, which is coming up next week with Caroline Gillis. Okay, thank you so much, everybody, and thank you so much, Vincent, for your presentation.
Thank you.
So now we get to just smile at everybody as they leave. That's the best part.